Today we're going to cover deformation and strain. So first let's go through some quick definitions. Deformation, whenever you apply force to a body, it tends to change the body in shape and size. Pretty straightforward. So normal strain, it basically just makes your body either longer or shorter. So this means there will be a change in volume. Like if you have a cube and it gets shorter, your volume is going to decrease. So if we look at the equation for average normal strain, we have the new length minus the original length divided by the original length. So it's length over length, so it's dimensionless. Shear strain. So it's a change in the angle between the original line segment and the new line segment, and you'll see what I'm talking about when we do an example. So this typically changes the shape, and this is our equation, pi over 2 minus theta. And the units here are radians, so you're going to end up having to convert from degrees to radians. So the plate is deformed into the dash shape shown. If in this deformed shape horizontal lines on the plate remain horizontal and do not change their length, determine A, the average normal strain alongside AB, and B, the average shear strain in the plate relative to the X and Y axes. So we're looking for two things, normal strain and shear strain. So we have this original square, and then, is it a square? No, it's not a square, it's a rectangle. And then it gets shifted slightly. So, I kind of redrew it to make a little bit more sense out of everything. So original AB is 250 millimeters. What we want to find is the new AB prime. That's the new length of the shifted line segment. And it shows us that it was shifted over 3 millimeters and shifted down 2 millimeters. So if I draw a new kind of triangle that relates all of this stuff, I end up with a 3 millimeter triangle, or a 3 millimeter length here, and 250 minus 2. So this is going to be the length here. And what I'm looking for is AB prime, and I can use Pythagorean theorem to find AB prime. So a squared plus b squared equals c squared. 250 minus 2 squared plus 3 squared. So the length of AB prime, this hypotenuse, is 248.018 millimeters. So from there, I use the equation for normal strain. So new length minus original divided by original. So the original length of AB was 250. So I end up with normal strain equals negative 0.00793 millimeters over millimeters, or you can just leave it dimensionless, it doesn't matter. So I end up with a negative normal strain. What does that mean? That just tells you that if you're negative, the line segment where the body was not compressed, maybe shortened and contracted. If it's positive, it means it was lengthened or elongated. So here we're contracting segment AB. Alright, so we have normal strain, now we want shear strain. Alright, so I kind of redrew the picture once again. Here's the original with the new one, then the new one, and my triangle that I deduced from the changes in dimension. So I have this new triangle, and what I am looking for is the shear strain. So the shear strain is the angle between the original line segment and the new line segment. So I'm looking for this angle in between here, this angle which I call phi. So typically, shear strain is found by taking pi over 2, or this 90-degree angle, minus theta prime. So here, theta prime is from the new segment to the x-axis, but there's no way that we can find theta prime. So in this case, we just find this phi angle directly. So phi equals arctangent of x over y. So I'm just doing opposite adjacent. So opposite is 3 millimeters divided by adjacent, which is 250 minus 2. So I end up with arctangent of 3 divided by 248 millimeters. And that gives me a shear strain of 0.693 degrees. Now, shear strain is always in radians, so I go through the conversion of 2 pi over 360 degrees, and that gives me 0.0121 radians. So there we have it. We found normal strain and shear strain, pretty straightforward.